Hello everyone. What do you get if you integrate x power n with respect to dx? Well, you are immediately going to say you get x power n plus 1 divided by n plus 1. But how do you say that? Well, you may very well say that Newton gave us that formula. Arguably, maybe Leibniz gave us that formula. But remember, both Leibniz and Newton both are credited with the invention of calculus. But there are no authoritative explanations immediately available, or a completely intuitive perspective is immediately available. In this video, I will try my best to give an intuitive explanation of how do you get integral of x power n with respect to dx as x power n plus 1 divided by n plus 1. To start with, let us entile a set of coordinate axes. So this is going to be our y-axis and this is going to be our x-axis. Okay, now let us consider a simple function, y is equal to x. So it's a very simple function. If you say y is equal to x, it's just going to be a straight line at an angle of 45 degrees. That's our expression, y is equal to x. If you plot it as a graph, this is what you will be getting. Now, let us try to find the area below this line y is equal to x. Let us try to find the area below this line y is equal to x. To find the area below this line y is equal to x, it's very simple. All you have to do is drop a perpendicular from this point so that it meets at the x-axis. Now, immediately you can say that it's just the area of a triangle. So we can immediately find the area. It's simple. It's just the area of the triangle, right? Yeah. Or we can think of a completely different perspective. That is, the area below the red line is actually some fraction of this green's area, of this green rectangle. Is that correct? Area below the red line is some fraction of this green rectangle. But exactly what fraction? You are going to say the area below the red line. So I'm going to say it's the area below the red line. Red line is some fraction of the green rectangle. Okay, that is obviously true. I can say the area below the red line is directly proportional to the green area, right? It is directly proportional to this green area. Maybe if you want me to give the points A, B, C, and D, right? It is directly proportional. Definitely yes. Well, there is no secret here. It is just equal to 1/2 of the rectangle ABCD. So if you want to eliminate this proportionality sign, you have to introduce a constant. That constant is C, some constant, some fraction of this rectangle. Now I can say the area below the red line is the area of the rectangle A, B, C, D over 2. In other words, it's half the area of the rectangle. Absolutely no secret. There is no secret at all. Right? Now, what is the area of the rectangle? It's a length into height. What is our length? It is obviously the length is x. And what is our height? Obviously, the height is y. So the area of the rectangle is length, which is x, into height, which is y, divided by 2. But we know what is y. Y is equal to x. So x into x, that becomes x square divided by 2. Very good. There is a pattern that has emerged just now, and that pattern is, you see the number 2 here? You see the number 2. Now we can try for different cases, and let us see whether, if you're getting power 3, will we get in the denominator 3? Let us try that out. Okay. Now let us consider a new case. This time we are going to entile again a set of coordinate axes. This is our y-axis. This is our x-axis. Now I am going to draw a curve. This time it's not a straight line. This time it's going to be a curve, and that curve is y is equal to x square. Y is equal to x square. So now the question here is, shall we find the area beneath this red curve, y is equal to x square? We are going to pull exactly the same technique. The area beneath the red curve, right? The area beneath the red curve should be directly proportional to some fraction of this rectangle. Okay. Some fraction of this green rectangle. So that is the area beneath the red curve. So I'm going to write the area beneath the red curve is directly proportional to, in other words, it is some fraction of the rectangle. So if you want to eliminate this proportionality, you have to introduce a constant, and that constant can be c, some fraction of c, of this rectangle. Now it is area is equal to c into, what is the area of this rectangle? Okay, it's length, which is x, into height, which is y. So it is going to be x into y, that's right, and the area is some fraction, and that fraction is c, right, into x, and we have y is x square. So y is equal to x squared. So area is equal to c into x cubed. Now we don't know what is the c, but in the previous case, we know what was c. In the previous case, the c was 1 by 2. Maybe because we don't know, maybe because you have the power in the numerator as 2, so you can put the denominator as 2. Shall we pull the same technique? It is, maybe the power is 3, so we put the denominator as 3. But how do we know whether this is correct? Well, we don't know. We don't know unless you measure it practically. You don't know. So how do you measure it practically? Well, we can measure it practically, the area beneath the red line, by dividing this area into many small rectangles. And what you can do is sum all the area of the rectangles. If you do that, you will know the value of a. So a is a known value. Remember, a is not mathematically computed, but a is practically computed. We are finding the value of a practically. And after finding the value of a practically, now a is a known value, that is equal to c into x cubed, and x cubed is a known value. We are going to put a tick mark because if it is from 0 to 5, then x is 5. So 5 cubed, you know that value. So c is equal to area, which is a known value, divided by 5 cubed. I am sorry, it's x cubed in general, it's x cubed, right? If x is equal to 5, that's 5 cubed, so it's x cubed. Now, you can find the value of c. And the value of c will reach its true value once you divide divide the area beneath the curve into further small rectangles like this. And when you do that, you are going to find out that the value of C reaches 1 by 3 asymptotically, now you know there is a pattern. And what is the pattern? The power numerator, if it is 3, in the denominator, it is also going to be 3. Now let us look at the general case. Okay, here we go. Let me entitle a set of coordinate axes. This is our y-axis. This is our x-axis. And we have a curve which is y is equal to x raised to the power n. Well, it should be a red curve, so I'll draw a red curve, right? Which is y is equal to x raised to the power n, and we are going to find the area beneath the red curve. So the area beneath the red curve should be directly proportional to the green rectangle. Where is our green rectangle? Here is our green rectangle. And you know what is the area of the green rectangle? So it's directly proportional to the green rectangle. So if you want to eliminate the proportionality sign, you introduce a constant c. It's some fraction of the green rectangle, and it is area is equal to c into what is the area of the green rectangle? It's length, which is x, into height, which is y. So it is x into y. And you know what is the value of y? Y is equal to x raised to the power n. So area is equal to c into x raised to the power n plus 1. Now we know what could be c is n plus 1, because you try this for a spectrum of curves. Y is equal to x cube means the value of c becomes 1 by 4. Y is equal to x power 4, the value of c becomes 1 by 5. Y is equal to x power 5, the value of c becomes 1 by 6. So there is a pattern. Mathematics is all about pattern. So you are tempted to put y is equal to x raised to the power n plus 1 over n plus 1. Why is that? Because we know practically that power in the numerator also appears in the denominator. We know that practically. This may be one of the ways in which Newton could have computed the formula for integral of x raised to the power n. With respect to dx, it is x power n plus 1 divided by n plus 1. What about differentiation of x power n? What about integration of sine x, integration of cos x? What about those formulas? Well, Newton definitely was a giant. Newton invented calculus but didn't talk about it to anyone for 27 years. Newton invented gravity, but he didn't talk about it to anyone for 10 years. Newton was a shy, self-effacing person. Just to explain gravity, Newton came up with a concept of calculus. Newton clearly was a giant. Okay. Anyway, we are trying to understand what those persons, what those giants actually invented. Thank you for your time. Much appreciated. Thank you so much.